Hello and welcome everyone to the November 4th Geometro webinar. Thank you so much everyone for logging in early and testing your equipment. That will ensure that you have the most benefit from this webinar, because that way Aniceta can look at everything that you're doing and give you direction and suggestions, and you guys can learn from each other, which is why we do this. Today's opening code is PRISM. P-R-I-S-M, PRISM. And without further ado, I'm going to hand this over to Aniceta Skowron. She is the creator of the Geometro, and I'll let her finish introducing herself and get teaching.
Hey, good afternoon, everybody, and welcome to this afternoon's second already webinar for the teachers of Florida. My plan for today is to show you ways how to use Geometro with little props and additions to teach three-dimensional geometry concepts, difficult concepts, in an accessible way. So here, let me start. Here is the plan for the workshop. I have three parts. First, we are going to be building some pyramids and prisms and other solids that might be a little bit new to you, so that you have a big arsenal of structures that you can present to your students and work with, make it exciting, more exciting than so far. Then we will go to the main body of the webinar, which will be modeling of 3D problems, modeling of concepts, and everything will be touchable and doable and very accessible. Then in the end, when I have a little bit more time, like a little bit, I'm going to show you what other things we could be studying with Geometro and what other things I have to show and tell you. I won't be able to this afternoon because it's only 1 hour and a half, but maybe if we plan a seminar together, like in person, then we can do those bigger things for a day. So just to give you overview so that you can have idea if you want it or not. Okay, so let's go ahead. What kind of problems are we going to be kind of touching here? I will be talking about Euler equation and how to use solids to actually play with the Euler equation. Then I will show you how to label solids and how to show all the distances in solids, how to model word problems. Then, of course, that will involve making Pythagoras triangles and getting ready to explore area, so getting all the distances and everything ready for formula if you have, and the same with volume. Then we will talk a little bit about diagonals and show diagonals. We will talk about directions in solids, and then I will show you how to directly measure volume of prisms and pyramids. Then we will touch on nets of 3D solids and cross sections if I still. Okay, so let's go ahead. First thing that we will do will be building the solids. First, we will do very simple, but then I will ask you to kind of get out of your box a little bit and use a little bit different procedure for building solids. But we'll get to that. Okay, so first, build this. When you are building with Geometro, I don't know if you've ever used this or not before, but you have shapes like polygons, and they have velcro at the edge. There is a hook, the hard part, and a soft fuzzy part. It's a loop. So the only thing you have to do is touch loop to hook and hook to loop. That's like that. It's enough. They will stick. We don't need to overlay, but it's very important that it's hook to loop, loop to hook. Otherwise, the solid will not stick. Okay? So go ahead and build that solid, and then we will have a little bit of a question and answer around this, on the topic of the solid. Okay? And I am going to watch you now doing this, so that this one is very easy, but I would like to have a practice in watching you. Okay? Okay, who is that? Michaela, right? Okay, you made something, but not what I was asking for actually, but good enough. because I want this. Okay, I can see Teresa, right? Wonderful. You made it. Now, what is this solid? Yeah. Here, Cynthia, what kind of shapes did you use at the bottom, Cynthia? Is it the same as on the picture? And anybody else will show me the structure, the solid? Good, wonderful. Anybody else? Make sure that you are using a pentagon for the base rather than a hexagon. Okay, you made this one, but for now it'll do. It's just that pentagon was supposed to be in the base, right? Who is here at the corner? I cannot see that all of you doing this yet. Okay, if you lower your cameras, maybe some of you, so that I can also see your work. Be nice. I can see that there is a little bit of overload on this thing. Okay, now let's talk about it. If you were to give somebody an instruction to make this solid, what would you say? Maybe I could have somebody, one person, kind of give me an instruction to make it. Okay, is anybody volunteering? How would you make it? Is there anybody eager to talk?
Okay, I'll try.
Okay.
I'll try. I would call it, is this like a pentagon prism? Is that what it's called?
Yes, it's a pentagonal prism.
Pentagon prism. And so it's different than a plane shape because we're going to give it dimension.
Okay.
Yes?
Okay.
So I would actually have the student start with the bottom flat, then build up the side, then I would have them build up the sides, and then put the top on it.
Okay, so basically you would attach squares to the side, right?
Squares to the sides.
And go ahead and make this whole thing, right? That's super. That's a perfectly good instruction. Most of the people give me this kind of instruction when we start. But I would like to introduce a little bit different way of doing this instruction that's going to be beneficial for the future and for making other solids. For that, have a look at the vertex of that solid. Here you have all the vertices, right? So look at the vertex and tell me what shapes come into contact in the vertex. So what is in the contact of the vertex? Anybody volunteer?
So we have the pentagon and then two squares touch at each vertex.
Is every vertex like this?
Yes.
Is every vertex the same? Yes.
Yes.
Okay, so now how could I use this idea of the vertex, that there are two squares and a pentagon in each vertex? How could I use this idea to give an instruction? What could you say? You could start with, build me a structure that, anybody?
You could say, build me a structure that has, using 2 pentagons and 5 squares.
No, I want a vertex.
Okay.
That has what in the vertex? So build me a structure that has...
I got an idea.
Yes?
Build me a structure that has 2 squares at every vertex.
2 squares and a pentagon.
Not at every vertex. I'm sorry, my speaker.
The instruction, a new kind of instruction that we could use is build me a structure that has 2 squares and a pentagon in each vertex. You know, this is a very good beneficial instruction for your students, especially because they are probing very locally. So if they can focus on each vertex without even knowing what they are building, they will still build this, right? So how about we practice some more, and I give you a different instruction, and you build a solid using this different instruction. So you now build something else. You don't know what you're going to build, but it is going to be very similar instruction. Something like this. Make a structure in which one pentagon and 3 triangles meet at each vertex. Okay, so you need to take apart what you have here because you only have 2 pentagons there, but just build it. And if you put cameras a little bit lower so that I can see, maybe I could, like if there is some problem brewing, I can spot it quickly. So we have gone and 3 triangles at each vertex. Okay, yes. Haley, I love the way you set up your camera because I can see what you are doing. Very good. Now, once you've done one vertex, just look at another vertex of the pyramid, of the pentagon, and go build 3 triangles there. And the next vertex of the pentagon and 3 triangles there until you go all around that pentagon and build all up those triangles. And then use one on top. Okay? Yes, Donna? Yeah, you have. Show me a little bit more of your camera. Like lower. Okay, in between those 2 triangles, you need to put a 3rd one. Okay, yeah, no, don't touch those triangles yet because it's only 2 now. Open them up and put 3 at the vertex. Oh yeah, put a 3rd one in between. And in between 2 triangles, you put a 3rd. Put a 3rd in between. You have like this, put a 3rd here. Here. Like this. Okay? Like this. Oh yeah, exactly. Yes, exactly. Now you have 3 triangles and each one like that. Each one like this. So next one, and on every corner, you build the same. Wonderful. I'm very happy how I can see you. Wonderful. That's already done. That's already done. Done. Wonderful. Now, Michaela, right? Okay, I watch you, but I don't see exactly where you are. And Cynthia, could you show me what you are working on? Could you lower your camera a little bit? No, she doesn't hear. Wonderful. Everybody is done. Okay, almost, yes. So now the question is, we built, what could be the name for it? And how is it similar or different from what we built before? So basically, we have built before, we have built this, which was pentagonal prism, and now we built this, which is something else. Now, what are similarities and differences between those two? First, let's talk about similarities. What's similar about those 2 structures? Very good, Donna. Very good. And now put one more triangle and one more pentagon on top. So what are similarities between those? What are similarities?
On top and bottom.
Yes, pentagon on top and bottom. Yes. And what is the relationship of those pentagons? They are
At the
parallel, right?
side.
Parallel. To one top and bottom. They are parallel in both structures. What are differences?
The sides are made of different shapes.
Yes. Here they are square. Here squares. Here they are triangles. Is the number of sides the same? No. Is the number of vertices the same?
No, there's more.
No.
There's more.
Can you count? Can you count?
1, Oh, maybe they're equal. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
There is
10
10.
vertices.
It's very simple. It's pentagon on top, so it's 5 vertices on top and 5 at the bottom. So here if you say like that, so it's 5 at the top and 5 the 10 here. So the last thing that I want you to mention is like in this one, you have those pentagons, they are just shifted like that. They have the same orientation, right? And here, the pentagon, here it's like this, but the other pentagon is rotated. Shifted and rotated. This one is called pentagonal prism, and this one is pentagonal anti. So now we have kind of discovered another kind of solid, which is the anti. Right?
Hey guys, I'm going to pause you for a second. I'm sorry, Aniceta. I'm getting a lot of feedback. And I can barely hear now, and I'm sure it's the same for everybody. And Daniela, I think it might be my mic. And every time I try to mute it, I cannot mute it. Sorry, give me 2 seconds. Okay.
Difficult moment when
I'm not sure what happened, Daniela, but yours like the mic is still on.
Happens, Daniela, but yours like the mic.
Everybody could please mute their mics. Hey Daniela, I'm sorry, I don't know what's going on. It just keeps coming back on. It's okay, Daniela. Technology.
It just keeps coming back on. It's okay, Daniela. Technology. What I'm going to do actually...
Yeah, I can't overwrite it. I'm going to take everyone's mic rights away. I know that's not what we want to do, but we'll have to probably use the chat box and raise your hand and I will enable your mic. It may take us just a few seconds longer, but I think that will help. So let me go ahead and now I don't hear it. I don't know if it's because I'm talking, but I'm just going to go ahead.
That's why you don't hear it. Okay, I think that this was my attempt to actually make it as interactive as possible, but it's actually not that easy. But we went through the kind of questions that I wanted to ask you in building the new kind of solid by looking at the vertex. And maybe I will not pursue it too far now, because if we get together, we will get to build other solids using this rule. You already know the rule, you can always do it, but I guess going at it right now might be a little bit more difficult. So here we have the prism and antiprism. I was planning to build more antiprisms, but I've actually skipped that. I will just tell you that those solids that we looked at that have the same vertex everywhere, like all the vertices, they are called Archimedean. So the sides, the faces, don't have to be equal, they have to be the same as long as the vertices are the same, like in all those solids. Those are called Archimedean. So now there is a question for you. If you look at the pyramid, so build yourself any pyramid that you can see on that picture. And the question is, does this rule of having the same value for the whole solid hold for the pyramids? So can you use this idea of the instruction of the same vertex for the pyramids? So a pyramid, Archimedean solid. And once you get the the pyramid done, you can kind of shake your head this or that way to indicate if they are Archimedean solids. Okay, so is that pyramid that you built an Archimedean solid? Yes or no? You can use the chat box actually and give the answers and we will read them. Whatever you think. Is this pyramid Archimedean solid? So are the vertices the same all over the solid? And no, I can see yes. Raise your hands and give me. Okay. I have one answer already, and you can put your answers in writing into the chat box so we can discuss that in a moment, right? Okay, so for example, let me now go over it quickly with all of you. Here is a pyramid, like any, just example. So if we look at the vertices at the bottom, they have two triangles and a square each. So those vertices are the same, but this vertex here has just the triangles. So they are not the same. So pyramids are not Archimedean solids, right? But now I would like you to look at those pyramids in a little bit more detail. And my question is a little bit of exploratory here, and I will look at your work on your desk, because what I want you to discover is how many different pyramids can you build using equilateral triangle? So how does it go for the triangles? What kind of pyramids you can build using triangles, like equilateral triangles, okay? So start building them, and let's see how many you can build different. Okay, I can see here there is one with pentagon, the one with triangle, okay. At the bottom, yes. So yes, you have here triangular pyramid. You have I can see square pyramid. I can see pentagonal pyramid. What else can we do?
I thought we lost you for a second, Aniceta.
Yeah, I noticed. Okay, then. So everybody, in the meantime, when I was gone, everybody built those I can see how many did we build. So we have pentagonal, we have square, we have triangular. Now, okay, yes, now I am very curious about this hexagonal pyramid. What happens when you use 6 triangles? Yes, I can see somebody has built something with 6 triangles, right? Oh yeah, here. You know what? This is something that we need to discuss seriously. 6 triangles. Here it's 6 triangles. Can you see 6 triangles? And what can you say about that? This is flat. This is flat. This is triangles, and they have 60 degrees each. So there is 360 degrees here. So this is flat. I can see people working on actually putting it together to the pentagon, but this is a little bit deceptive, because for the reasons of constructing, the triangles that are used for Geometro are a wee bit bigger because they are too pointy otherwise. So that's why you could kind of, what you are doing, you are just basically bending those triangles to force them on this hexagon. But the thing is that you are not able to build a hexagonal pyramid with equilateral triangles because this angle is 360 degrees and it's a flat shape. Now, just to make it a little bit more visible, could you build me a pyramid using octagon and equilateral triangles? You have an octagon in your pouch, in your big bag, so use either octagon or decagon, the big one, and use equilaterals and try to build a pyramid and see if you can do this. With equilateral triangles. Why not? I can see some heads turning. And what's going on here? Yes, I can see highly, right? You've done something different. I wanted you to take the base, which is the octagon, and use this to make triangles, to make pyramid, like something like this. Okay? Oh yes, exactly, yes. I know what you started. You started from the vertex, right? And it showed that it's possible, right? So actually I never thought about doing it like this, but you did it also very nicely. Yeah, I'm going to use this idea as well. Never thought about it. Yeah. Okay, so we can see, I cannot hear you now, not so easy, and I don't want to mess up this audio again. So I will just show you, and maybe we can just kind of do it this way. You can see that those triangles are not far enough, not big enough to connect, right? So this cannot be built using equilateral triangle. And what is the moment, what is the structure that is the border one? First you can, then there is a border, and then you cannot. So the one that is the border is the hexagon. This is the hexagon. So this is where it first stops to be possible, because then they become flat. If you put any more, then they become, then you start to get this. They don't even touch each other. Here, they just touch each other, but they are flat. Here, they cannot even touch themselves. So you can see that for pyramids, there is a limit. There is a condition that limits the number of pyramids. Here, I put a little bit of a summary of this for you, right? So with pyramids, you can build a triangular pyramid using equilateral triangles. You can build triangular, you can build square, you can build pentagon, and then with a hexagon, it's flat. It's 360 degrees, and you cannot build any more, because after that, the case is like this. It's too little. Okay, so now let's move on and look what happens with these isosceles triangles. What is so maybe let's start from the other end. How many triangles you would have to use so that you have a flat thing, so something similar to this, but using the isosceles triangles, the ones that you have. So we will look, right, when it's flat. So see when it gets flat, and everything less than that will be possible, or then we can discuss, right? So find out the flat thing for the pyramid. Okay, so how many? How many did we use? Huh? Yeah, I like Haley. Yeah, because and here Teresa also did a nice. Everybody, yes, they are coming to the same. Okay, here is why I gave you so many of those triangles, just to show you this, right? So that you can see that if you have 12, I think how many is there? I think 12. That's the last one that you can build because you cannot squeeze anymore. Can you see that? So this one is still possible, but anything more than that is not. Let me count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yeah, okay. So 12 is still possible, but 13 would be already too much. So you can see that for every base, there is a limit on how many pyramids you can build. So if you look at that shape, like if you want to use this shape for the bottom, then the smallest pyramid triangle that you would have to use is this, right? If you use this triangle, exactly, then you would have a flat shape. And all triangles that are bigger than that will produce a pyramid. Okay, I just wanted to make this point because we talk a lot geometry about triangles, how to construct triangles. Then when you have a triangle, sum of two sides have to be larger than any third. And it's similar to building the pyramids because basically you have also triangles there, right? Okay, so here it's a little summary for you. Here it's how it goes. With pyramids, we get only 3 pyramids with the equilateral triangles, and we get more depending on what kind of triangles we use. But the ones that we have, the last one is 12, and then 13 we cannot build, right? Now I would like also to show you one more different kind of structure that children make a lot, and it's very easy, and you can play with this with your students as well. Basically, make yourself 2 pyramids without bottoms, like square pyramids, using any triangles you want, either isosceles or equilateral. So 2 square pyramids. Okay, you have 2 square base. You don't have to use the bottoms. Don't use the bottom. Open the bottom. No square. Just the top, just the sides of the pyramid. Or something like this, just without the bottom. Just 4 triangles and a square pyramid without the bottom. And you make 2 like that. Okay, and now what you do, you have 2, everybody has 2, yes. Once you have 2, what you do, you mirror, like in a mirror reflection, you touch both of them. You make 1. Yeah, so you have this. And now you can do with any pyramid like that. You can do it with a big pyramid. Okay? So 2 pyramids that are joined by their bases, but they don't have bases, but just joined like that, by pyramids. Okay? So by pyramids, you have any pyramid without the bottom, and you just touch them together. It's a nice shape. Again, kids make it a lot. So now you have 4 kinds of solids, right? that we could work it. And I wanted just to say one more thing, that with making those bipyramids, of course, the same kind of limits apply to making pyramids, right? Because you only can make 3 out of equilateral triangles and many with isosceles, right? But it's the same idea, that because you have limits on pyramids, you would have limits on bipyramids as well. But what I wanted you to have now is an arsenal of structures and names for them that you can use with your students and play. So you have prisms, you have antiprisms, you have pyramids, and you have bipyramids, right? So it's a lot to play with. Okay, now we are going to change gears and we will go into modeling and showing what you can do with this. Now you have some structures to play with, some interesting new names and structures, and now I would like to show you what we can do with that. So let's start with Euler equation. Okay, Euler equation, I am not sure that you use, it doesn't show all of it here, but never mind, I don't know. Euler equation joins in an equation number of vertices with number of faces and number of edges. So this equation gives us an excuse to count number of all those numbers and explore the solids. But for students with vision impairment, it is sometimes difficult for them to count because they need some kind of markers for what they have counted, what they haven't. So say we have a prism and we want to count the number of faces. So for this, as a marker, I bought, this one is in dollar store, those jello kind of plate, you know, like things, and you can put them on top, right? And you can take them off, you can put them on, and then you can mark the faces that have already been counted. Alternatively, if you have a lower vision student, you can use that dry erase marker and mark, okay? Or you can use any other sticky marker, provided it's not too sticky and you can unstick it easily. So here is how you count, you know, like mark the faces. How do you mark the edges? You have those pouches, take them out, with those little pieces of velcro. Okay, take them out. Take any of those structures that you have right now on your desk, if you have anything built, any of them. And now let's mark some edges. To mark the edges, I use those small little ones, the orange, and you just place them right in the middle, like, or wherever. They will stick because they will stick somewhere to the... So that way you can just go and count and mark all the edges that have already been counted. Okay, easy enough. Now you also in the pouch have those light shapes, okay, like that, pieces of velcro. Those you bend in half like this, and you stick them to the vertex like this, like ear. You kind of earmark the vertices like this. Okay. So that way you have all marked edges, vertices, and faces. Here is how you do it, just a little reminder on this. And now what you can do, you can now use this equation. You have to add number of faces to number of vertices and take away the number of edges. You can use this formula and get your students to check for any given solid. You can use any solid, or you can build up a table for different solids and then get them to discover if this is all, discover the pattern. It's a little bit more difficult maybe for older students, but for younger you can just check the Euler equation if it holds. Now, question to you. Does the Euler equation to a cylinder and a cone? I would like some of you to type in the chat box to see, because I want to know if this apply, if it does, why, if it doesn't, why. Very simple sentence. Okay? Daniela, no, I can see, but I think it might have been a previous no. Is there a new no now? And if it's no, why it's not? They just typed. Oh, they just typed no. Okay. But why not? Anybody can say why not? No, because the surfaces are not flat. Yes, true. Yeah, that's. But even bigger idea is that here one of the surfaces for a cylinder is what? Is a circle, and circle doesn't have any vertices. So the Euler equation only applies to solids that are built out of polygons, which is like they have this one does it's not a polyhedron because it doesn't have polygons. It doesn't have sharp cornered shapes for the spaces. So circle is not a polygon. That's why it doesn't apply. But also because it's curved, it's curved because it goes around the circle, and circle is not a polygon. So that's how it goes. Okay, so good answer. Labeling solids. Now, when you have problems like square, like you have labeled vertices like A, B, C, D. Now, how we could do this? We could do it easily. You have those velcro pieces in your pouches like this, right? So what you have, you just undo them, whatever color is there. And we will do it in a moment. You cut them into smaller pieces and you use marker to write A, B, C, D on them. For example, like here, I have one that is marked A, B, C, D, and the one that you see. So that way you can mark every vertex and really any place that is important in the problem that you are working with. You can see, so that I kind of showed you some labels. Now, connectors, very important thing. For this, you have in your pouch some straws, drinking straws, and you have some paper clips that have velcro at the end, like that. Right? Can you see? Oh yeah, here. Yeah. Okay. So what you do with this is you take a straw, and at the end you actually insert that paper clip into the straw. So if you used loop, you use hook on the other side. Hook and loop. One goes one, and the other goes the other one. So then you have a little rod with sticky ends. Of course, you could also do something that I did before. I mean, I just glued immediately on the straw. But if you do this, you don't waste your velcro. It's very, because you can always take it out, right? And you can use different length of the straw. So now if you make a few like that, I have 2 or 3, so I can now make any triangle and it will stick. I can build triangles, any kind triangle that I want, because now I can cut those straws any length I need, right? Now, how this is going to be used within structures, within solids? Well, we have problems sometimes. They ask us to build something, to show something. So here, for example, I have this, but I also build it. Here it's some kind of nondescript problem, but here I have built a triangle inside that cube. And because say that I had a problem that I had to do it, right? And now I can even open this and I can put inside, right? I can take it out, I can put it on the desk, I can put it back. So you can see that I could cut to pieces whatever I need for a particular problem. example of problem in just one moment after I show you all the tricks, and then you will get chance to use those tricks and to build for yourself. Okay, so here it's the next little trick that you could also use. You know, if you have low vision students, you can obviously also write on this. You can take the dry erase marker and you can write the distances that are needed right on the cube. Okay, whatever is easier. Another little trick that you can also use, and I have it in here. Uh-oh. What happened? Andrea? Ooh. Okay, so this one doesn't, I don't know what happened to the slide, but never mind, it's not that important. I can show you here. What you can also do, you can, instead of using the Velcro with the paper clip, you just can use just a plain paper clip, just plain paper clip, like this. And if you have any magnet, what you can do is secure this with a magnet, okay? So it will stick on top, okay? So those are the ways of doing this. Now, I have prepared two problems right at the next slide, and I want you to pick one of those problems and make a model for that problem. I give distances in the problems. Those are not your concern. You don't have to measure and make it the same. I just want you to make an illustration to that problem. What kind of triangles you would have to use to solve that problem. That's a typical problem in maybe grade 6, 7, maybe, you know, when they start coming, like in a little higher elementary school. But for you, it is practice to label and to actually make an illustration to a particular problem. So here they are problems. You have a cube, A, B, C, D, and A prime, B prime, C. And I give you the length of that cube, the edge length. And I want you to make an illustration to be able to calculate. So make a triangle that would be appropriate. Knowing the length of the edge, go to diagonal. If you don't like this problem, you can pick next one. In the next one, you have a hexagonal pyramid, okay? And you have given the length of the edge of the hexagon. And I want you to find out the triangle that gives the dimensions of the triangle. So either height or the edge, whichever is easier for you, okay? So go and build me the model. Label everything, use those straws that you have and the paper clips to put it together to make the triangle, okay? I'll be watching and we will convene in 2-3 minutes, maybe 5, to see how you've done this problem, okay? Everybody go to work. Yeah, you will need to cut those straws to this size. And remember, they have to be cut a little bit shorter than the actual size because you have to allow for those ends, which are the Velcro, so 5 millimeters or so for the ends of the Velcro. Okay, you will find your way because you will experiment with it, cut it. Maybe you can cut a little bit more after a moment, but I want that illustration of that problem, any of those problems. I can see lots of people working with a cube, not so many working with the pyramid so far, which is fine, which is gorgeous. Yes. Yeah, this straw is just good enough for the diagonal. So if you put the paper clips right at the ends, they will kind of lodge there, and you only have to measure the other two. Yes, brilliant. Yes, I can see this here. Wonderful. You know, yeah, gorgeous. Yes, I can see it was Haley, right? And Teresa is getting there too. I just see only one distance, right? Teresa, I want more distances, because now you have you modeled the diagonal, but you haven't modeled the edge, because I am giving you the edge. So from the edge, you have to get to the diagonal. So you have to use a triangle. Maybe, oh, you drew on it, right? I don't see exactly if you drew on it or not. Yeah, Haley did a very good job. Yes, I like that. Yes, wonderful. Yes. Okay. Yeah. And where is the edge? How do you model the edge, Teresa? If you perfectly good way, but if you now wanted to touch everything or take it out, it would be probably easier if you had all straws. I suggest you start with all straws, because that's, yeah. So make a triangle. Okay, wonderful. Very good, very good. Now I made a model here myself too, so I can see that all of you are very close to the same idea. Yes, you can see what I did. Okay, oh yeah. You know what I did as well? I put in red the distance that was given in the problem. Okay, so this focuses attention, you know, if you have, or you can make it I don't know how you can texturize that. You probably have your own ideas how to texturize for students who do not see at all. But this is, and how did I make this? This is very easy. When you have straws, I use the electric tape, and I pull out some of it. You pull out some, and then you put that straw on that and just roll it. And then you have a nice color. Those tapes come in different colors: white, blue, green, red, orange, whatever. So it's very easy to make all this really colorful and you know, color coded for whatever you need. So here it is, right? You can take it out. Here is the distance that we want. Here is the distance that we are given, and here is the distance that we need, kind of, it's an intermediate that we have to get, right? This distance first, you know, this is all now mathematics, and I am not here to teach you mathematics per se, because I am assuming you are good with this, and we just need to have the ways of showing how it could be visualized and made tactile. Now, for the other problem with the pyramid, what I gave you was the edge of the pyramid, right? So here it's the same one as this, right? Because it's all equilateral triangles. So what is given is the red one, and we want the height, and the height is, we want the height. We have the height, and I actually should have given you the height as well. And this is now what we are looking for, right? So you can see that you can model it like that. And from the edge, you can also calculate the height of the triangle. So the idea here is not so much the the steps to calculate and to get this mathematically, but to actually get the idea of how to build it and how to show it, right? Okay, so I made a mess. Here I have this idea of how to use those tape and the straws and the scissors to actually make them colored, any color you need or you like. Next. Again, also I wanted to show you how to build those paper clips, because I gave them to you. They are not so much work, but you know, you need to be, I just wanted to share with you how I do it. Here is a piece of velcro with a glue on top, right? So what I did, hang on in the camera, I put as many, I mean, I think it's 5 or 6. I'll show you in a moment. I place them like this. I'll just show you in a moment, hang on. I place those paper clips like this, okay, halfway through the velcro. And then you close the velcro and then cut them. And then you will have as many as you like of the kind that you like, right? So this is how to make those paper clips, velcro, so that if you need more for whatever you are doing. Now we switch to something different. We'll talk about orientation of lines, okay? Parallel lines, perpendicular lines, and skew lines. So let's look at the cube again. Have a cube, you know, you can remove everything from your cube, take that cube, and you have those velcro rods. You have those velcro sticks that in your kit. You have 3. I can't remember, you have 3 or 2 probably. Like that, you see them, right? So now I would like you to use those to show me direction of the cube. So I would like to show pairs of parallel lines, then, and what? Yes, oh, exactly. You just touch them to the edge. So pairs of parallel lines or pairs of perpendicular lines, okay, of skew lines. What are skew lines? Skew lines are the ones that are not parallel, but they never touch, they never cross. So yes, so you have to, if you have one like this, you have to find one that kind of goes in a different plane, that will never cross, but it's not parallel. I want you to find out. Oh yes, I can see one example. Beautiful. Yes, yes, yeah, exactly. Okay, also worth noting is that the parallel are not just here, but also here, right? Those two. So here it's what you use for that. Now, how about parallel lines in pyramids? How many parallel lines are in a pyramid? Do you have any pyramid on your desk? Can we talk? Yeah, I can see hexagonal pyramid. And anybody has a pentagonal pyramid or triangular pyramid? So yes, you have some lines, but how about pentagonal pyramid? Do you have pentagonal? Or triangular? Yes, okay. How many parallel lines in triangular pyramid? Yeah, there is none, right? So with pyramids, it's a little bit different because we have the parallel lines if they are present at the base. But if there is no parallel lines in the base, then there are no parallel lines in this. Now, this pyramid, you have those triangles as well. I have not used those shapes so far, but you have those big triangles. They are really very special to Florida because they were made just for you guys. So you can also make this kind of pyramids and investigate all the parallel lines in this pyramid as well, and all the rest, right? Okay, so we have the direction of lines. Here is the summary: parallel, perpendicular, and skew lines. How many pairs of skew edges are? So build yourself tetrahedron and show me 3 different pairs or 4 or however many different pairs of skew edges. Okay, wonderful. How many are like that? You know, I just had this idea. I had already, when I was practicing for making the velcro with colors, I already have lots of different colors of that. So I could show you. You don't have that. But what you have is those pieces. So you can also mark them like with the whole thing. But you can use those pieces to mark pairs as well. Okay? Or you can even use those, right, to put markers on appropriate pairs, right? So what I did here with the Velcro rods, because I could, I had different colors. You don't, but you are resourceful and you can find different colors with different ways, right? Wonderful. Yes. So we have 3 pairs of skew edges in the tetrahedron, right? Okay, so this one sums up directions of lines. Now we will go to diagonals. Okay, very easy. How about we go back to our cube? So take away all that you have right now, put away those Velcro rods for now, and make yourself a cube. Make yourself a cube, and you have all those red plastic rods. Use those to show me diagonal in the cube. Okay, this is one. I want many. I want all of them at the same time. Okay, everybody done? Wonderful. Okay, I show you one more trick, because what you would probably like is that your students put hands in, right? So that you want them to probe it and touch it inside. So if you open one of the flaps, one of the things, they will fall out, those top ones. So you can use this white piece of Velcro just to secure it to the top. Okay, so it sits here, and then you can safely open the flap and get them inside, right? So you need to kind of look at that, see which ones you want to open, which one needs securing, and just go for that. That's a trick, okay? So you can see that we can have how many? 4 diagonals in the cube, and they meet in the middle at the center of the cube. They cross at one spot. Of course, you don't, because otherwise they wouldn't be able to pass, but you can kind of model that or imagine it. So, okay. Now the question for you is, now if you build pentagonal prism again, okay? So we done the diagonals in the cube. I wanted you to do the diagonals in pentagonal prism, okay? So now take it all off and build your pentagonal prism and put diagonals into pentagonal prism using the same methods. So basically undo your cube, undo your diagonals in the cube, and get busy with the pentagonal prism. By the end of it, you are going to be so good at pentagonal prism. Pentagonal prism. Which one was the pentagonal prism? Guys, I can see you using something that is not going to get you pentagonal prism. Here it's pentagonal prism. You use squares for the sides and a pentagon, not a hexagon, pentagon. So pentagon at the bottom, squares at the sides. Now, of course, you can use rectangles for the sides, okay? Because I didn't say it was square pentagonal prism. You use either rectangles for the sides or squares for the sides. But you have to use pentagons at the bottom and the rectangle or square at the sides. And make sure that you have a pentagon at the bottom. It doesn't matter if it's, for the exercise, if it's a hexagon, but we need to be precise in using pentagon when I ask for pentagon. So pentagon at the bottom and the squares for the sides. And then you use all your sticks to put the diagonals in. Okay, so you can see now that it's becoming a little bit different exercise. It doesn't look quite the same as it looked for this cube, right? First difference could be easily seen that they do not seem to cross at the same point in the middle, right? They kind of pass each other and they do not quite cross like they were crossing in the cube, right? And there are maybe different number. How many do you have already? Yeah, you can, where's my pentagon here? So how many will we have? You know, how we could calculate that? I mean, we can put 2 from the vertex, right? We put 2 from each vertex. Then we have 10, right? Hang on. Okay, so the idea here is to actually show you that those diagonals are not, again, they have more complexity than the diagonals in the cube, right? You can put many of them, and they don't have to cross each other in the center. There are other things happening for those diagonals, right? We could have the exploration exercise with your students, like you can order those solids by the bases, like the bigger base, and see how with the change of the base there is change in the number of the diagonals, right? So there are exploratory exercises that can go with this. But do with you now though is to make a pyramid. Okay, so make a pyramid, say hexagonal or pentagonal, any one that you like. Say make this one, and put diagonals into this pyramid. So we can cover both prisms and the pyramids. So make this pyramid now and show the diagonals in this pyramid. Okay. Okay, I can see people already finished building and now starting to put the diagonals into the pyramids. That's really interesting, yes. I can see, I give you one more moment and then we will, like, I see what you are guys doing, and we will just talk about it in just 1 second or maybe 1 minute. Okay, let us now talk about it. Now here, I can see you are putting it many different ways, but I know that I cannot hear you. This is the moment when I actually would love to have feedback from you and a live discussion. That's where it gets difficult because we cannot quite talk. But I challenge you on this. Like, look, here in the pentagonal prism and in cube, those diagonals, they were going through the body of the solid. And here with this exercise, we are really touching on the heart of the matter. Basically, what is a diagonal? What is a diagonal? How we define a diagonal? So now listen to what I say. A diagonal is a line that joins two vertices of a solid, but cannot coincide with the face, cannot sit on the face, and cannot sit on the edge. Okay? So now look at these ones that you made and see if you made diagonals. Diagonal is something that goes through the solid and then joins just two vertices. That's it. Two vertices, any two vertices. But it cannot be on the edge, it cannot be on the face. So how many in this pyramid? I want answers in writing. How many diagonals in this pyramid that you have? How many diagonals there are? Those are lines that join two vertices but do not sit on a face and they do not sit on an edge. show me one like that, or many, or write me how many of those you have. Please type to me. I want a number. Good job. Yeah, exactly. There are none. So pyramids don't have diagonals. You can see how much you can kind of play with this and what kind of thinking goes into this. You have to be, it gets curious and more you work. Of course, also, it would be interesting to look at this. We're not going to go through it, but that's another one that you can go and inquire how many diagonals you have here, right? So that's why I showed you all those different solids, so that you can extend that thinking and that inquiry to different solids and probe if your students understand the concept. Because if you give them always the same, you are not going to spot if they understand or not what the concept was. So here are the questions and the issues with the diagonals. First of all, we need to get into definition. Something that goes through two vertices but doesn't lie on the face, doesn't lie on the edge. How many diagonals in each polyhedron that you can probe as well. Now, what are the patterns between those diagonals? And do they cross? How they cross? Where they cross? So all those are questions that you can probe with your students. Now, measuring solids. Okay, so now I would like you to maybe put this away, although you might not be at this part, because I did not give you all the things because it would have been too difficult for me. But I will show you what to do, and you can then emulate that on your own. So first of all, distances. With building those straws, it's very easy to actually get the distances, right? So to show your students which distances you need, right? If it's a height or diagonal or whatever, then they can measure it, like first make it, then measure. But measuring volume is quite interesting. For this, what I have is the following. I have those are the packaging styrofoam peanuts, and I cut those peanuts into little pieces, like each into 3 pieces, so that they are small, and the smaller the better. So now what you can do is actually, like you are filling sometimes the shapes with water, you can fill say I want to measure the cube, I can fill cube. Oh my goodness, I haven't got enough. If you just wait 1 second, I have more here. So you're filling that cube with those peanuts, and then so now you have the volume of the cube filled. And now what I did, I bought, and you can also buy it, I mean, you have to look for it, I bought it on Amazon. This is a cube tray for making ice, but it has the property that it's cubic inch. So the edge is a cube inch. So this one is each enter is a cubic inch, and you can then now transfer from, instead of measuring the volume through a beaker, which has the scale on it, and it's not as direct. This one is really direct because you then count how many cubic inches there is. The problem with this is that it could produce a big error because you have to fill it, the smaller the pieces, the less error. But anyways, you can do it like very conceptually, that, how many cubic inches, how many pieces you can fill. Now, you can also make solids like prisms, pyramids, and cones, and transfer between them. For example, I can make a cone, make a pyramid and a related prism, they are not exactly equal. This one is a little taller because they have equal sides, but it's almost good. So what I did is you could again fill this one up. This. So this is the volume of the cone of the pyramid, and you transfer it. Oh my goodness! Transfer it to the. I have to catch some of it. Right? So you transferred it, and now you can see that if I mark the level here, it's almost a third. Right? So this shows that the volume of the pyramid, the same height pyramid as the prism, they have the same 1/3 volume here of this. And of course the same applies for the cylinder and the cone. So you can now transfer those peanuts from cylinder to cone, and you will again show that it's a third to volume. So this is the measuring of the volume. Now I would like to show you something about a little bit different, which is oblique solids. Solid that is not straight, like in a cube you have all edges perpendicular. But what happens if you want to slant? That's another way to show the volume. Here I have the size of it too. Okay, so for this I need those foam squares. Okay, so I have foam squares, and each square is 11.2 centimeter, and I make them such that each color is an inch. So you have an inch, so you can see quickly now that the volume of this is 4 and a little bit of cubic inch. Now, what if I wanted to make it skew? So what you have to do, take away some and then do this. So you can see that this is now oblique. So it holds fewer of those squares. It now holds only 3 inches. And also another thing that I did here, I had a paper measuring tape from IKEA, not just a paper. So I rolled it together, like glued it together, like into a cylinder. Took my old drinking straw and a paper clip, and paper clip I bend 90 degrees like this. You stick it inside, and then you can fix it in here. So then you get a measure of the height. You see? You can show that it's always vertical because it will stay vertical. And now you can see that you can measure the height, right? And now if you can remove another inch of the foam, okay. You can see now the height is smaller and the volume is smaller. Now it's only 2 cubic inches, and so on until you actually can remove all of it and fold like this, and it's 0. So it shows how the volume gets smaller because of the height gets smaller. We have the same base, right? The base is all the time the same. It's just that the height gets smaller and smaller and smaller until it's 0. It's another way of actually, well, conceptualizing the idea of the relationship between volume and the height of the prism. Now, you can also make use of those straws in another way. I have pictured it here. Okay, here it's a close-up of that ensemble, and you can see how those get smaller and smaller, right, until they go to 0. Now, what we can do also is, like, if you take, say, 2 squares, and here I have those straws that I have on. I just glued velcro on those, and I can attach them like this, like it shows on the. You see here, and then they connect to the bottom on the next. In the moment I show you. Right. So now. So you don't use all the Geometro for all of it because that limits you, right? This gives you a little bit more options because what you can do is this, right? You can show, or you can do this, right? Or now it's all very movable, and you can do a lot with this, right? You can also do this. So you get quite a bit of geometry playing. And by the way, this, when you twist it 90 degrees, it's the same thing that we did right in the beginning, the anti-prism. Because this one is when the sides are parallel, and now when they are twisted, right? So here it's another way of actually showing more complicated solids and more variety, more excitement. Here I'm showing this now. Okay, so we now got into nets. You have done nets, guys, right? Quite a bit. Here's the first exercise that I usually do with children. Like if we have a cube, how many different ways there are to undo the cube, to make a net of a cube? How about you make a cube yourself and draw 3 different nets for the cube? 3 different ways to undo the cube. So once you do this, you could make a little drawing and then do another one, make a little drawing. I did this with a grade 2, and we had to find all those ways. There are 11 different ways to undo the cube into a net. So when it gets to 7, 8, it is becoming more and more difficult to actually come up with a new one that wasn't already on the blackboard because we were drawing them on the blackboard. It's quite an interesting exercise because children have to be able to distinguish when those nets are flipped, when those nets are rotated, right, on different orientation. They have to be able to recognize that topologically they are the same thing, right? So you have those 3 different nets already. Here is this exercise done by teachers. Okay, so I guess maybe we already kind of went through this. The interesting thing about those nets is that obviously when you are doing it this way, like when you have a cube and you are undoing the cube, you cannot really go wrong. But when you have squares and you want to make a net, you could make something that is not necessarily a net. For example, something like this. Would this be a net? Could we make it into a cube? If I try, I cannot bend this anymore. So basically, not every arrangement of even if I had 6, I had 5 here, but even if I had 6, it still wouldn't be good enough because of this region here. right? So not every arrangement of 6 squares will give a net for a cube. And this is the basis of exercise for children, right? Here I give you 11 nets. You can actually order them. So there is a pattern into those nets. You can get that on internet very easily, so there's no need to worry here. But here it's the idea of the jumped on me, of the wrong nets. So you have arrangements sometimes that are not nets. So the exercise for a child would be to discover if something is a net or not, and if not, why not, and how to correct it. Okay, so this was the basis, and of course, you do it with a cube, but you can do it with any other solid because every solid has a net and many nets. So this is an exercise in recognizing the properties of those solids and nets and how they all are related. So here is a little book that I made, like a compilation really of some nets that are good and no good for each of the simple solids. And the children will color the ones that are good, and the ones that are no good, there will be another page where they have to say how to correct it, how to make it better so that it could be a net. Okay? Now, there was the APH was very interested in making this into a tactile book for students. So we say, well, okay, let's do it. Let's make all those nets in tactile drawings and all the rest of it. But I had a problem because and at the beginning of those pages, I would have the picture of the solid and then the nets. And how do you give a picture of a solid to a vision impaired student? Tactily, drawings of 3D figures are very difficult, and it's very difficult for students to actually recognize. So this was the idea, to make a special kit, special manipulatives to actually help with that. And I will show you what's the problem. For example, if you have a cube, right? All the edges are the same, all the angles are 90 degrees, and it's right? But when it's a drawing, it's not 90 degrees. Not all the edges are even. And in a picture, you see the same. It's all because of perspective, right? Because it comes from the fact that in perspective, parallel lines don't stay parallel, they diverge in a distance. And so the cube can be drawn different ways, depending on how many parallel points of parallelism you pick. For 1, for 2, for 3, that cube becomes more and more like what we have. This comes from the fact that our retinas are flat. And all the pictures come on our retina, and it's make a flat impression. And then it goes back to the visual cortex, and visual cortex actually interprets those images, puts it back together, and we quickly realize that it's a 3D from those subtle cues on perspective. So our brains actually compute it back, and we have no difficulty in looking at this flat picture and reading it immediately as a 3D picture, which is not the case for visually unexperienced impaired students. So what I wanted is to make something that will give them idea of how this happens, how this flatness happens, flatten those shapes so that they look like the drawings, okay? So here is my attempt. I'll show you on a cube. Let me just find out the cube here because I used up all my cubes. Hang on. Okay, so here is a cube, and I have those. This is what I call rod model. What first happens, I'll show it to you here. We put it on top of the cube like this. So, but then we take it out, we squeeze it, and we do this, and it now looks like a drawing, right? So the student can actually pick what is up, what is below, right? So they can probe that this is higher, this is lower, and so on. And in this kit, I'll just bring it in a moment, just 1 second. What happens is that we have then a drawing, and it's a tactile drawing of the cube. That model thing here fits on this, like this, okay? And that can be put up and down as many times as you want until you get the idea that why this is so weird, because you have to put something big and bulky, 3D, into 2D. That's why it's so funny. So this is exercise for the cube, and then you have the two cubes, like one beside the other, because you can do it two ways, right? And then the students hopefully get some idea why this is so difficult. And I show you on pyramid. Pyramid is even worse than cube, because I made a cube very simple, but pyramid, I mean, you can see pyramid here. Like to make a pyramid flat, what you have to do, you can see the red pieces and the one marked green. So the green is at the back. And the back one has to get shorter, and those one have to get longer, and then it goes flat. You can see? And now you can see something that looks like a drawing of do it again, and it's a pyramid, and put it back again, and it's a drawing, and so on and on. So this is a piece of equipment that will get those students thinking of why. It's still difficult for them to read the 3D drawing of pyramids, say, but at least they might have a concept why it's so difficult. And then what happens that we made also like the drawings of the nets. Those are drawings of the nets. They are tactile, and here are little pieces of magnetic tile that have raised edge, and you can put them inside. And this is the metal board. So here, some of those nets are good, some of those nets are bad. And then once they do this, they can transfer it to Geometro to build this with Geometro and discover if it's possible or not possible. So here is the preview of this kind of the product, really, because I just wanted to show. If you need it, you can use it, and maybe we could have a chance to play with it next time when we get together. So let me just go back here. I think I have a little drawings of all the same, so I will just go through it. You can see how you put it on the cube, how you then twist it, right, stretch it and put it flat. And you can put it flat this way or this way, and you can do the same with a pyramid, right? So it looks like a pyramid, and you can put it up and down, and then you have the whole kit. Here is the broken and dotted lines. Like, again, on the drawings, you have broken lines and dotted lines. And why this is happening? Because here is another model that I made. This is the same cube, and when you put it flat, you can see that those spaces obscure what goes on at the back. So that's why you have a broken line and you don't see this, right? So you can have another model for showing what's happening. So you can see that in the dimensionality is very important in tactile drawings, and it's something to talk more and make it easier. Now, we will not, I'm just looking at the time, now it's 15 minutes left. We do not have much time to go through cross-sections, but I will just point out how to do it if you have students that would benefit. So say you have a cube and you would like to show cross-section of a cube. what you would do is you can have elastic. I'm not sure that I gave you elastics, but I cannot remember. So you could just model cross-section with those elastics, like this. Okay? So any cross-section that you need to show can be modeled using the elastics. You have to watch so that it's like really flat, so that it doesn't go, wayward, but you can model this. If you need something smaller, I used elastic with a little velcro on top, like put velcro on the elastic, and then the velcro would, I'll show you in a moment. For example, if you wanted how to cut a corner in the, can you see this? Okay, so there. I just keep this, and here is the future. So what would be the topics and plan for a seminar that if we get together, so you can kind of see if you would be interested in this. I would get you play with this, because this set is new and it probably is worth playing so that you get ideas from that. Then we would use the same strategy that we used in the beginning of looking at the vertex, and we would build variety of different solids. We would build platonic solids, and we would build very exciting, very nice Archimedean solids. And here it's a picture of another group of teachers that we built it all together in a I can't remember, it was 2 or 3 hours that we built it, but it would be incorporated if we had a day or so. That's what we would do. We would do projections of 3D shapes. You had that on tests quite a bit, and that is better for vision impaired students, but I didn't have the pictures yet. So that's what we would cover. We would do cross sections in a bit more details. Then we would do cross sections of cone and cylinder. This is a topic for high school students. So if anybody of you has high school, there are also nice ways of showing tactily how to do the cross sections of cone and cylinder. And also I would talk about symmetry, about how to cut those shapes into halves and use mirrors to show mirror symmetry, and how to rotate them to show the rotation symmetry. And then I would give you a whole spiel on how all those solids come into inspiration in science and art and engineering. And that's a very nice one. I didn't have time to do it, or we didn't build those solids, so you were not really inspired by the solids themselves. That's why I don't do it right now. But we could do that. This I skipped. Now here is a contact to get some more information. Here is the here is the contact to get me. I would be absolutely delighted to hear from you and to see how you enjoyed the seminar, and if you have any questions or any concerns. And now I would like, maybe you have some questions. I would be very happy to entertain the questions from you. Otherwise, thank you very much. And I think we are a little bit ahead of time, but if you want some questions, I would be very happy. So any questions, you can type them to me, and I'll be very happy to answer.
There we go. Hello. Oh, now my microphone's working.
Yeah. Question is the cylinder and cone part of the kit? It is a separate kit. Actually, it's the newest product. We shipped just the first shipment was in summer. So in the fall, it came in with APH. APH is the distributor, and I think it's on the quota funds, the cylinder and cone, because it's new. So you can get it. From what I understand, it's already on back order. So yeah, but we will be shipping more very soon. So it's there. You can get it from APH. Another question. Not many yet. Okay, if there are no other questions, yes, Andrea?
Well, while let's see. Oh, Daniela said, thank you, Aniceta. No questions from me. Yay. Thanks, Daniela. I know you had a little trouble in the beginning, but I'm glad we could get you on and make it work. Thank you, guys. I know it's Friday afternoon. We really appreciate you joining us and playing along. I love the straws and the paper clips. I really just think those are such simple, easy adaptations. And we told the group yesterday, Kathy Krempleski and I were just blown away at just how easy and simple it was. We're like, oh, geez, you know. So I just love all these ideas. And the Geometro can be used to develop so many different geometric concepts, problem solving, and critical thinking that our students really need to be involved in hands-on, and that's why we really wanted to bring Aniceta so you could see the different ways you can utilize the Geometro. And remember, you're going to be working with your math teachers. I mean, if they're willing to use it and implement it with all students and use it with your student, let them roll with it. I think it's a fabulous way to make the student a part of the classroom. But yes, and Aniceta also kept referring to a possible face-to-face seminar, and what we're looking at is next year for working with the experts, we would like to bring Aniceta in face-to-face so we can actually focus on STEM and have Aniceta come and do a hands-on workshop face-to-face. So we would love to have her come back.
It's a fantastic way to learn from you guys, because you know you toss those off comments that oh, how about this, how about that, and it's now you cannot talk to me. So for me, it's a great relief, because I learned so much from you, from those seminars. I see what you do, I see what you ask, and it's incredible, because that's how I get my inspiration. So that's why I be personally very happy just to share what I know, but also to learn from you what you need, because that's equally fascinating and important. So thank you very much. I enjoyed meeting you, and I really like this format. It's the first time that we did it this way, but I think it works great, except that I cannot hear you. Thank you.
Thank you, Aniceta. Okay, so real quick, guys, I know you want to hustle out the door. I'm going to have you do the survey real quick, and I'll give you the closing code. So I'm going to open up the survey. You guys could answer these 5 questions for me real quick. I really appreciate it. It's all those wonderful questions that are required by the Florida Department of Education to show that we are doing what we are supposed to do and why we are here. And the closing code is Pentagon. Closing code is Pentagon. So yes, we really look forward to having Aniceta back next year for working with the experts, and we'll cover scientific talking calculators, geometros, maybe even embossing with the TI-84 from not Freedom Scientific, APH, all that good stuff. All right, it looks like I've got all the answers. Yes, sharing with the high school geometry teacher is great. I think that geometry teachers would definitely help you run with this stuff and help develop concepts for your students. Oh, whoa, a whole bunch just showed up all at once. Y'all must have typed and hit enter at the same time. Perfect, awesome. Thank you, guys. I'm going to close this out and go back to sharing. Thank you for your input. And as always, you can always email us with questions and comments and anything else you guys need. So yeah, so thanks. Oh, Tiffany, you raised your hand. Yes, ma'am. Go ahead and type in the chat box. I see Hallie typing. I'll go ahead and stop recording, and you guys can feel free to ask some questions.